Okay, so we'll start. Hello, everyone. I'm Kailas Prasad, PhD scholar from Nano Electronic Devices and Circuit Lab, Nano DC Lab, we say, at IIT Gandhinagar. And welcome to live session 3 of Design and Analysis of VLSI Subsystem course taught by Professor Madhav Rao. So we have this session every Tuesday from 7 p.m. to 9 p.m. According to Indian Standard Times. So the goal of this session is to supplement what that has been taught in the class, right, with questions. And my another goal is to make sure that you understand whatever concept that has been taught in the class with greater detail. This is a platform to openly ask questions. If you have any question, you can ask me, or we can have an interaction session over here. Okay. Also, I've put a couple of questions which are actually generally asked in interviews whenever you will apply for any of the big MNCs in VLSI design like Intel, NVIDIA, ARM, or ST Microelectronic, NXP. You name any company. The basic set of question which will be asked from VLSI we are actually similar. Okay, so I try to cover all of this, some of those questions actually in this particular session. So I encourage everyone to join this session, and if you have your friends who are also studying VLSI, preparing for VLSI interviews and all, or are interested in VLSI, please encourage them to join this session. So we will start today's lecture. So as of now, so we are in week 3. So in week 1 and 2, what we have done, we have learned the basic of CMOS transistor. In the very first section, we have understood about how the MOSFET works, right? And on the basis of that, we have solved many of the questions. In week 2, what we have discussed is about inverters. We have seen inverter characteristics and all. In today's lecture, our main goal is on noise margin of inverter. So the questions which I put forward are on the noise margin. But before starting that, I wanted to show you a couple of slides which are actually recently presented in various top conferences like IEDM or IMEC or IRPS. Okay, so this is one of such slide. This is a potential roadmap extension which has been presented by IMEC. IMEC is one of the leading research institutes in VLSI domain. This is based in Belgium, right? And what they are forecasting, okay, down the line 10 years or 15 years, how our transistors will look like. Okay, currently where are we? We are here at N5 and N3. Okay, so I will, yeah, change the color. So we are at N5 and N3. Okay, so here we are currently using FinFETs. So these are the transistors we have been using for past say 15 years. Okay, down the lines 10 years or 15 years from now, the same architecture we won't be able to scale, right? So if you want to have faster and faster performance from your transistor, you have to change the architecture itself. So there are a couple of architectures which has been proposed in literature, and the companies like TSMC and Intel are extremely and aggressively working on it. So the three companies, I would name them. Okay, so the first one is Intel. Okay, the second one is TSMC, and the third one is Samsung. Okay, all of these three companies are aggressively working on new architecture of device, which they call as actually the general name is GAA. Okay, you can see over here, gate all around. So gate all around we say. Okay, and also it many people say it as nano sheets. Okay, how does this work? I'm not going that into detail. I'm just telling you, okay, what is coming ahead in next 10 to 15 years. Okay, so if you want in greater detail, maybe we can have an offline discussion, or you can throw me a question. I'll be discussing about how the architecture works. So, but the thing is, what Intel say, Intel named this kind of transistor as ribbon FET. Okay, so in I think last year, Intel has shown their roadmap, and in their roadmap, they said that in the latest technology they will have, and they have named that technology as 18A. Okay, so as of now, whatever technology you might have heard, right, it is in nanometers, right? It is 180 nanometer, 130 nanometer. If you are coming to recent, it is 5 nanometer, 3 nanometer. But the thing is that the nanometer era has gone. We are here at Armstrong era. Okay, so now they are actually naming all the nodes as Armstrong. Okay, so Intel is naming it as 18 Armstrong. Okay, 1.8 nanometer. Okay, the TSMC call it as nano sheets. Okay, so they have not changed their name, and Samsung call the same architecture as MBC FET. All of this actually follows this gate all around. Okay, gate all around structure, and all of these three companies are extremely and aggressively working on having next generation of CMOS technology. TSMC and Samsung has actually reported it. Okay, in next year, by the next year, whatever devices that will be made might have this kind of transistor. Okay, as a VLSI engineer, as a devices engineer or a circuit engineer, you should know, okay, what is going on and what is coming down the line 10 years. And apart from that, till say what is it is, right? So 16 angstrom or 14 angstrom, they projected that okay, they will be using gate-all-around structure with slight modification. Now, after that, people are planning to go for different kind of architecture, and these architectures are CFET. These are called as complementary FETs. Complementary FET, right? As of now, whatever transistors we have, so whatever logic we design in digital design, right, there is a separate NMOS and separate PMOS, and both are fabricated side by side. Okay, NMOS is at different place and PMOS is a different place. If you see over here, it is either NMOS or a PMOS, but it is taking a lot of area, right? So the idea is, can I reduce the area footprint? So people are talking about this kind of structure where NMOS will be here and sitting over top there will be PMOS. Okay, this will be NMOS, this will be PMOS. People have demonstrated this complementary FET in research. This is not in mass production. Extensive research is going on from all of these companies and various leading institutes in India and the world. Okay, so you should know what kind of advancement which we'll be seeing in next 5 to 10 years. So just a brief potential roadmap extension of IMEC. Any question in this particular slide? Okay, so moving to another announcement. This recently I just came across, so I just plan to put over here. Okay, so you might know that currently everybody is talking about autonomous cars. Okay, Elon Musk, Tesla is one of the leading companies in self-driving cars and autonomous technology. But the thing is, whenever you are trying to design autonomous system, you require chip. Okay, so that is the basic thing in the autonomous or self-driving car. Right? There will be a control system, or there will be a controller chip which will actually control all the decisions that you will be taking. It should be extremely fast. It should be extremely energy efficient. These are the two requirements which have. And the third requirement, whenever we talk about self-driving cars, is it should be extremely reliable. It means that every time it should give you correct output or whatever you are expecting. So in the self-driving car case, right, you the expected thing is you move right, and if it suddenly moves left, right, then there is a problem. Okay, this kind of failures can occur due to software algorithms, but it can also occur due to hardware design also. If your hardware fails or hardware is giving erroneous output, so whatever technology that will be employed in self-driving car or that are employed in self-driving car should be extremely reliable. It should be extremely fast because the decision has to be made in split seconds. Along with that, it should be extremely energy efficient, because whatever self-driving car you are running, it is actually operating in using some battery and all, right? So the energy consumption should be down. So this recent announcement that has come. So Umbrella is actually one of the companies which design chips for autonomous cars, and Samsung is one of the foundries which I have told, right? And they have been collaborating with long time, and they said that okay, the new Umbrella chip, which will be actually what they say as CV3AD685. Uh, and it actually advances autonomous and advanced driver assistance system. Okay, because a self-driving car will have some system. This system they are talking about, and the Samsung will provide a single chip solution for that. Okay, for multi-sensor fusion and path planning. It means that whatever decision that will be taken, that will be taken by this chip, and this chip will be fabricated in Samsung 5 nanometer. So this is again a recent news. You should follow whatever going on around in the semiconductor, such that you'll be motivated. Okay, these are the two news I just wanted to share. Now, what I will do, I will move to today's class. Okay, before proceeding to that, if you have any question, feel free to ask. Okay, so we will move. So this is the most basic circuit in the digital design, which I'm talking about is inverter. Inverter has a PMOS, there is a PMOS, okay, and there is an NMOS. If you provide 0, it will give you 1. If you provide 1, and the output is 0. Right? Very simple circuit. Now, what we will do today is we will try to answer some of the basic question, and I want everybody to participate. Okay, so these questions are for you. So I want answer from you. So this is the question from previous class. What happens when PMOS and NMOS are interchanged with one another in an inverter? Hello. Can anybody answer this question? The first question I'm asking that what happens when the PMOS and NMOS are interchanged with one another in an inverter? Anyone?
It's what as a buffer, but called the bad buffer.
Yeah, thank you for the answer. So it will act as a buffer, but it will be a bad buffer. Okay. So why I'm saying that, I will just revise if you don't remember. So it is like this. So it will be like this one, and so this will be your inverter. Okay. So whenever you provide 0, okay, this transistor will be on, this transistor will be off. The output will try to go to ground, but you know that whenever PMOS is connected and PMOS doesn't pass as 0, right? PMOS is very bad at passing 0, there will be a VTH drop. So if circuit's VDD is 5 volt, okay, and VTH N and VTH-P, okay, mod of all of this is 1 volt, what will happen whenever you provide 0 over here? If my input in and this is output y, input is 0, what will the output? I will answer that question, Raja. But before that, what will the output of this? If I am providing input 0, what output you are expecting at y? 0. It will be 0 volt. So in terms of volt, I want. Okay. Anybody want to answer? The output actually won't be 0. Rather, it will be VTP. Exactly, right? Because there will be a threshold voltage drop. So the answer will
Zero
be,
point 0.3 volt.
yeah. So in my case, it is 1 volt. I'm saying
Yeah, this is, oh,
so
sorry,
it
sorry.
is 1.
This is
Okay.
1.
Yeah, you're correct. Now, if I provided instead of 0, I provided 5 volt over here. Now, what will be the output?
This is 4.
4. Okay. So the thing is, whatever input you are providing, it is going to output. It is acting as a buffer, but your output swing has reduced. It means that if you have provided like this, if this is your input, now whatever output you will have, output will be like this. Okay, so it won't be a good buffer, right? It's a bad buffer. How a good buffer look like? Can anybody answer me? How do we design a good buffer?
By using two inverter back to back connect.
Exactly, right? So what you have to do, you have to use two inverter back to back. So this is how you design a good buffer. Okay, because now you will get the full output change, but you are using four transistors. But yeah, that you have to pay the penalty. Okay, so this was the question from the last class, just to make sure that you remember from the last class and all. Okay, now what we will do, we will move to the first question which we have and today's class. So please read the question and try to answer. I will make the figure. What happens to delay, right? What happens to delay if you increase the load capacitance? So if this is my inverter, suppose, okay, and if this is my load capacitance CL, okay, so what will happen to the delay if I am increasing the load capacitance? The delay increases. Does anybody has a contradictory opinion? Will delay increase if I increase the load capacitance? Okay, Aditya is supporting. What about others? Very simple question. Just want to know. You can comment. Okay, I just have two answers. 10 people over here. What happens if the load capacitance increases? Anybody else? Delay will increase. Okay, Pankaj is also saying delay will increase. So yeah, it will increase, right? Because the tau is equal to RC. Okay, whenever the capacitance increases, the delay will increase. So that's a simple argument. Okay, and again, the next question will be followed by this only. What will happen if the resistance of the at output increases? Okay, so again, this question also, the answer will remain the same. Okay, because either C increase or R increase, the output delay will increase. Okay, now I have a question that if I want to reduce the delay of this particular circuit, okay, if I want to reduce the delay of this particular circuit and consider that I do not have any load over here, okay, can anybody tell me what are the approaches I can apply if I want to reduce the delay of the circuit? The question is clear, right? The question is what are the approaches to reduce the delay of my inverter? This is my inverter. What are the approaches? Anyone?
By changing width of the MOS
By changing width of the MOS, should I increase or decrease?
W uh, W to decrease the load, decrease the W.
Okay, you are
Actually,
saying
the
that W should be decreased. Okay. Any other way by which we can change or reduce the delay? Other students? Okay, so let us focus on this particular argument. So it's a fair argument in the regards that okay, the concept behind why I should reduce W, because the node capacitance at so is actually what, right? So the node capacitance comes from the drain of the
it
PMOS
is W.
and the drain of the NMOS and the width, right? So whatever if the width is large, the capacitance will be large. If the width is small, the capacitance is small. Okay, but I just want to ask if this argument is completely correct. Anybody has a contradicting opinion about that? I agree that if you reduce the width, the capacitance will go down. Okay, TL will go down.
Increase with
Sorry,
increase W.
you're saying increasing W. Okay, okay, I have an
Yeah.
alternative argument. Why should I increase W?
By increasing W, we have smaller resistor.
Smaller resistance. Excellent.
Yes.
So R will go down. So now I have contradicting opinion. Okay, so one is saying that I should decrease W because the capacitance will go down. The other argument is you should increase W because in that regards R will go down. So the thing is there is not correct width which is actually available, right? Because we want higher W such that your resistance is less, right? Such that your current is more because current is directly proportional, so inversely proportional to the time. But the thing is, at the same time, if you increase W, the capacitance will also increase, right? So the thing is, you have to find an optimal point where your W is providing you an optimum delay, right? What I mean that whenever you will, so if this axis is W, okay, I'm making a very rough graph, and if this is your delay, okay, what will happen to capacitance if I increase W? The capacitance will increase, right? What will happen to to resistance if I increase W? The resistance will decrease, right? What will happen to delay? Because delay is tau times RC, right? Delay is tau times RC. So the delay will be like this, and there will be an optimum W where the time is optimum. Okay, so the answer to my question was that you do not know actually, right, whether increasing W is an option or decreasing W is an option. You have to actually find out an optimal point where, because both the parameters are changing. Everybody agrees with that? Whatever argument I have made, everybody agrees. Okay, Momita agrees. What about others? Okay, okay, thank you. I have lot of agreements. Now, I think I had one question from Raja. What will happen? What will be the output if both the transistors are on? Okay. So let us see. Let us try to answer this particular question from Raja because he has put that question in the chat. So what is the question? Question is, I have a PMOS and I have an NMOS, and this is an inverter. Can anybody tell me what will be the case if this is my VDD? Okay, this is my ground, this is my input, this is my output. What value should be in input such that both PMOS and NMOS are on? Anyone? VTH. VTH of what? NMOS or PMOS? NMOS, okay. What about others? Any other argument? Okay, so yeah, that's a correct argument, right? If the VGS of both NMOS and PMOS are nearly equal to VTH, mod of VTH, okay, in that point, both NMOS and PMOS will be on, okay, partially on. Now, that point actually generally comes around which voltage? VDD by 2. If you keep your input as VDD by 2, what will happen? Both NMOSes and PMOSes are on in that point. Okay. What is the beauty of the CMOS circuit and what is the basic advantage of the CMOS circuit? Because CMOS has been, I think, identified way back, 40, 50 years back, right? People are using still CMOS circuit. What is the reason behind it? Anybody wants to tell me? What is the reason why people prefer this kind of configuration? One PMOS and another NMOS. Anyone? Rail to tail. Okay. I'm not understanding what you're trying to say. Okay. Rail to tail means VDD to ground. See, let me try to answer. Okay, let me try to answer this question. What happens in CMOS circuit if your PMOS is on, the NMOS will be off. Okay, and if NMOS is on, PMOS will be off. So in that regards, what will happen? There will be no direct path from VDD to ground in the static mode. Okay, so whenever your circuit is static, it means either the input is 0 or 1. You take any gate, you take NAND gate, NOR gate, XOR gate, whatever gate you take, your NMOS, if the pull down network, which is your NMOS based network, is on, the upper part will be off. And if the upper part is on, the lower part will be off. And because of that, there is a huge power saving. Okay, that's the beauty of the CMOS circuit. That's the reason why we call it static CMOS. Okay, now the thing is, when does the power consumption happen? So the power consumption actually happens when the input is transitioning. Okay, so that when the input is actually going from 0 to VDD. In the case of inverter, if the input is going from 0 to VDD, what will happen? The output will go from VDD to 0. Okay, and in this particular range, if you see in this particular range, the input is actually near VDD by 2. In that particular case, both PMOSes and NMOSes are on, and in that point, the power will be consumed. Okay, and what will be the output at that particular point? So if I am considering that you have taken care of the beta, if beta p and beta n, okay, beta p is equal to beta n, both the resistance are same, the output, when input is VDD by 2, the output will also be VDD by 2. Okay, and if it varies from any point, it will either go to 0 or go to 1. Okay, or it will be some intermediate voltage at that particular point, right? And this will be the point when the input is transitioning, the output will also be transition. Okay, and the power consumption at this particular time is called as dynamic power consumption. Okay, and this is the most what you say, contributing factor in the power whenever we have when we analyze this kind of circuit, right? So to answer your question, Raja, when both PMOSes and NMOSes are on, if input is at VDD by 2 and the beta p and beta n is equal, the output will be VDD by 2. If beta p n are not equal, so it will act as a resistance divider network and you can find the voltage accordingly. If you don't know the input, you don't know the output, right? But it will be between VDD, 0 to VDD. It will be an intermediate output. Okay, so you're talking about VDD by 2 is a metastable state or not? Okay, so see, metastability comes. Uh, so how do I explain this? So let me give you an example. Okay, so VDD by 2, why do we consider VDD by 2 as a metastable state? Okay, so we say that in generally we have three states. Actually, we have two states only. One is stable, another one is metastable. Okay, so let me draw the characteristics for you. So this is how inverter looks like. Okay, see, if this is V out, this is V in. Okay, if V in is lesser than this particular voltage, right, your output is 1. If V in is greater than this particular voltage, the output is 0. If V in is VDD by 2, right, the output is unknown. So in digital circuit, we have only two outputs, either VDD or zero, right? If you don't have your output either VDD or zero, you don't know what output is. Okay, and the thing is, if you are at this particular voltage and if you just move anywhere, okay, from here to here, either you will go to zero or go to VDD. You don't know. Okay, the noise will decide. If there is a positive noise, so it means if VDD Vin is increasing, right, so it will go to zero. If Vin is decreasing, it will go to one, right? The noise will decide. That's the reason this particular VDD by 2 point is called as metastable state. And please note, right, you have to take this argument only if beta p is equal to beta n. If beta p is not equal to beta n, then VDD by 2 won't be your metastable state. It will be some other voltage, which will be which will be exactly that point where the symmetric point we are talking about. Okay. Do you agree? Everybody agrees? So VDD by 2 at output is metastable state, but to get VDD by 2 output, what input you are providing, that will depend upon beta p and beta n. So that's what I am saying, right? So this is, if this is an inverter and this node is VDD by 2, then yeah, it's a metastable state. What input you are providing to get VDD by 2, that will depend on beta p and beta n. If beta p and beta n are equal, then you have to provide VDD by 2 to make this inverter metastable. If this is not equal, then there will be other voltage which will make output go to VDD by 2. Okay, generally when we talk about this circuits like this, which are combinational circuit, we don't discuss about metastability. We'll be discussing about what we call as SRAM. Okay, SRAM is a memory, or we will discuss about latch in coming lectures, maybe after more than I think after 6 or 7 week we will discuss this, right? We there I will discuss in detail about metastability, how does it work, and how can it affect your system, and how do you get out of metastability, and what kind of causes it will have, what kind of problems it will create. Okay, so I hope this thing is clear. Okay, I have more questions. Okay, I have more questions. Again, these are tricky questions which are asked in interviews, and I find this kind of question very interesting because, yeah, this will actually make you think hard, right? Why certain things are so. The question is, why is the substrate of NMOS is connected to ground, and in PMOS it is connected to VDD? Okay, it means whenever I design a transistor like this or inverter like this. See, I'm not defining substrate over here, right? It is an implicit assumption that in a digital circuit, this substrate is actually connected to VDD for this, and the substrate from here is connected to ground. Anybody wants to answer this? Why we do that? And please note that this statement is extremely true. In digital circuit, we do that, and anybody wants to answer? To reverse by the substrate with respect to what? To reverse by the substrate, that's correct, with respect to drain and source. And why do you want to reverse bias? So, okay, I have one answer: reverse bias, substrate. Okay, reverse bias substrate with respect to source and drain, right? And Raja is actually saying the answer, that to avoid leakage. Okay, I will just show you how it happens. So this is how your NMOS look like. Okay, this is your N plus, this is your N plus, this is oxide, this is the gate, this is substrate P. Okay, this is source. If this is drain, then if you make this to 0, your P side, right, there is the PN junction over here. You see, this is PN, there is another PN junction over here, right? If this is forward biased, what will happen? There will be a current which will be flowing from source to substrate. You don't want that. What do you want? Your current should flow from source to drain only. Okay, so this current should not be there. So that's the reason in the case of NMOS you make it zero. If you make it zero, your P side, right? For if this is a PN junction, PN, this is connected to zero. This will be connected to some voltage, right? Your this junction will be reverse bias and the leakage will be extremely less. So that's the reason why we make sure that your substrate in NMOS is actually connected to ground and substrate in PMOS is actually connected to VDD. Is that clear to everybody? Is that clear? Okay. What about others? Okay. Thank you. Now I have one more question. Okay. These are basic questions. Okay. But yeah, it will help us in understanding the basic. I have more questions also. Okay. So the question here is in the CMOS technology, okay, in digital design, why do we design or size PMOS to be higher than the NMOS? It's a very simple question. Can you tell me what are the reasons for that? So what we try, the WP is greater than WN. This generally happens. Why? Yes.
So to match the drain current for PMOS and NMOS,
Match.
because
Yeah, because
we match the drain current of PMOS and NMOS, because the whole mobility are less half of the electron mobility. That's why we required the width is more than double. Actually, width is required double for WP.
okay. Okay. Thank you. So the answer is again, yeah, that's correct. To match the drain current of PMOS and NMOS, right? And what he's saying is WP is equal to twice of WN. Okay. So this is on the assumption that mu P is 1 by 2 mu N. If this is the case, then WP is twice WN. Okay. Generally, this 2 times factor we take, but you should understand, right? While when you go and design, right? So it should not be like that. The mobility is 1 by mobility of P is 1 by 2 times of mobility N. Okay, it can be any factor ranging from 1.5 or 1.4 to 3. Okay, so mu P can be greater than, not greater than, less than mu N. Okay, and mu P by mu N by mu P can vary from 1.4 to 3. Okay, so the technology we currently use, I actually use, the mobility ratio over there is 1.4, and the other technology which I use, their mobility ratio is actually 2.2. Okay, so generally we take 2 because the older technology had that, but the thing is you have to go and find out the mobility ratio. It's an easy job, right? You just find out the current at the same width, and if you take the ratio, it will give you the mobility ratio. Okay, so I think that's the answer. Now because you have answered this question, I have a follow-up question that when you design transmission gate, okay, you size equally. So this is a transmission gate. Okay, this is a transmission gate, this is an NMOS, and this is a PMOS. Okay, and if this is X, this will be also X, right? Select bar. So in transmission gate, we try to size them equally. Why? There we are not changing W, or we are not making sure about this ratio. Anybody wants to comment?
Actually, transmission gate is work like a multiplexer. That's to pass the input from to output. Yeah. So for that reason, there is no need to. There is a current should be actually only to pass the output. So the current similarity should not be required. I think so. That's why it will be the W will be no factor there. If we consider a capacitor at the output, then passing the input to output means the charging the capacitor. Only the for NMOS will charge the capacitor discharge. Actually, NMOS will pass the zero, so it will be discharged faster, and PMOS will pass the one, so it will be charged the capacitor. So that's why the wheel is not required here. But for inverter, it will be important.
Okay. So the argument which has been made that NMOS is passing zero, right? It will charge this particular cap. So please note, whenever you design any digital circuit, there is associated cap with it. Okay, you can assume that because there will be associated parasitic capacitance. Now, if you pass zero from here, this you are actually you are discharging this cap. If you are passing one over here, you are actually charging this cap. And what he is saying that yeah, so because NMOS and PMOS are doing their job, so why do we need to size, right? Do we have any other argument from anyone more apart from this? Okay, so let me answer this question for you. So this is yeah, we don't tell or say this is a multiplexer. It's a switch. Okay, it's a switch. Okay, so if you give S, then if S is high, the output will be going. If S is low, output won't be going. Okay, so eventually that's a multiplexer only, but we call this a switch. The thing is, in this transmission gate, the NMOS and PMOS actually assist each other, right? So if you are passing zero, so it will pass through NMOS. Also, it will pass some of the current will flow through PMOS also, right? Because it's like PMOS won't completely pass zero, but it will pass zero up to a certain extent, right? It is assisting, the NMOS is assisting PMOS for passing one, and PMOS is assisting NMOS for passing zero, right? So there is an assist operation which is going on, right? It is helping them. While in case of inverter, there is no assist like that, right? So if you want to pass a one, you have to pass through only PMOS. If you have to pass zero, you have to pass through only NMOS. Okay, so and if you want to have same rise and fall time, you have to size them accordingly, otherwise it will be very skewed towards each other, right? While in the case of transmission gate, it is not the case. Okay, so that's the reason, because both of them are in parallel, right? Because of that, you do not require to size in the transmission gate. Required to size as mean PMOS and NMOS, there should not be, it's not like that, okay, the PMOS should be higher width or NMOS should be of lower width, right? You will increase the size of both NMOSs and PMOSs if you want to drive higher load, if you want to have higher current, but you don't size PMOS and NMOS unless and until there is another alternate reason for that. Okay. Any question in this regards? Any questions? Okay, so if you don't have questions here, so now we will start moving to our numericals. Okay, so I hope it is visible to everyone. I hope it is visible, right? In the diagram below, Mitch, what is A, B, C, and D?
Hello.
Yes.
नहीं आ रहा ना सुनो.
Sorry. Okay, I think yeah. So my question is, can anybody name A, B, C, and D? So see, there are four options you have. Which of them are which? Please note this is V in, this is V out.
Uh, Point A, VOH, output voltage high. Point B, VOL, output voltage low. Point C, VIH, and point D, VIL. Sorry, first one is the VIL. Point C is VIL, and point D is the VIH.
Okay, yeah. So everybody agrees with this? Everybody agrees? Just type yes if you agree. If you don't agree, type no. Uh, Everybody agrees with this A, B, C, and D, VOH, VOL, VIL, and VIH. Okay, Thian agreed. Okay, so what about others? No opinions? Okay, if you don't have opinion, I will tell you why it is like no or it is named like this, right? So see, this is output. Okay, so whenever we write V, right? So we whenever it is an output, you write O. So whatever there which is on y-axis, it will be O. Okay. Please note that this is a higher voltage, right? So this is the reason it is VOH. Then it is a lower voltage. Then the reason it is named as VOL. Output high, output low. Okay. Then over here, which is the lower voltage? This is the lower voltage, right? But it is an input. So VI input, but this is the lower voltage. So L. This is the higher voltage, but it is an input. So VIH. Okay. So these are the 4 points: VOH, VOL, VIL, and VIH. Okay. So now moving to next question, why these are important? Why I am saying this? So it will be actually coming into the next question. So this is the transfer characteristic of an inverter. Okay. And you see the values are given. V in is equal to 1.046 and V out is equal to 2.654. Okay, this is your first point, right? If this point is A, okay, if this point is B, so for B, V in is 1.531 and V out is 0.295. Okay, the question over here is what is the noise margin high and low? Can anybody tell me the answer? What is the definition of noise margin high and noise margin low? What is NMH, noise margin high? Should I call out name? Anybody wants to answer? Noise margin high? No? So, okay, let me write VOH minus VIL. So, this is noise margin high. Okay. And noise margin low? I've written noise margin high. Can anybody tell me noise margin low? So,
So VIH minus VOL.
that's VOL. Okay. High minus low. It is always high minus low. Okay. So, anybody wants to tell me the answer? So here, what is our VOH, VIL, VIH, and VIL? So we will first write out that. Okay. So what is VOH? What is VOH? You can look at the graph and you can tell me. What is VOH?
2.6
2.65.
low.
2.654. What is
54.
IH?
Point
VIH? VIH is
1.046.
no
Sorry,
VIH.
VIL.
VIH I'm talking about. Input high. This is
V VI. Okay, VIH is 1.531.
1.531. Then VOL. This is output low. This point
VOL 0.295.
95 and VIL. This is
1.046.
okay. So we will quickly calculate NMH. So this is VOH minus VIL. So VOH is 2.654 minus VIL is 1.046, and this will be how much? Anybody tell me?
1.608.
1.608, and NML is VIH minus VOL, right? So this will be 1.531 minus 0.295. This will be what?
1.236.
1.236. Okay. So yeah. So this is the answer. Everybody agrees with this? The simple calculation. Okay, so I will quickly move to next question, which is again a simple one, very simple one. Okay, so just read through it and just tell me the answer. Which one is the option? Okay, the question here says that which of the following seems like a feasible way to decrease the rise and fall time in a generic digital CMOS circuit? This I have already discussed, right? What I am saying over here that which of the following seems like a feasible way to decrease the rise and fall times in a generic digital CMOS circuit. So TR and TF, okay, rise time and fall time, you want to decrease. It means you actually want to decrease the delay. Okay, out of this five options, what do you think? Which option you prefer? Five. Okay, we have six, seven options. I have. Anyone? Anyone wants to answer? Just discuss, right? We have just discussed this, I think, a couple of minutes back.
Okay, A is there that we have discussed earlier. Decrease the size of the transistor used to reduce the input and output capacitance.
So this we have discussed, right? This we have discussed, and this also we have discussed, but these are contradictory statements. But this is not the ideal way, right?
Yes.
This, so what is the ideal way? See, anybody wants to answer? Aditya is saying E. Okay, Aditya is saying E. At least I have some answer. What about others? No answer. So Aditya is absolutely correct. Okay. So optimize the size of the transistor to increase the saturation current. So you want that the current should increase, but at the same time, the load capacitance should not increase. Okay, so I've said, right, this is my W, right? If this is my delay, okay, and in the same axis, if I'm plotting R and C, okay, so what will happen to R? R will decrease, capacitance will increase, capacitance will increase with W. So what you have to do, you have to find an optimum point where R and C are actually minimum. So you have to optimize this point. Everybody agrees with this? Not agreeing? Okay, so yeah, so that's the correct option, E1. Now we will move to another one. Again, a simple question. See, this is an uh, inverter which is connected like this. You just have to tell me what will be the C load, what will be the output capacitance. Okay, you see over here that WP1 is given, WP2 is given, WN1 is given, WN2 is given. These are the width. Okay, and you have to tell the answer in terms of C. You can tell that, okay, unit capacitance is C, so what will be the final output or the final C load over here. So this we have to find. Anyone? Quickly. What will be the C load? Okay, so let me tell you how do I approach this question. So if this is a node, it is connected to what? Okay, so it is connected to first drain of P2, okay, second drain of N2, third drain of, you see this node is also connected to this, okay, drain of P1, the fourth is again drain of N1. Okay, so it is connected to drain of 4 transistors, this C load. If you see what are the sizes of this particular yeah, what are the sizes of all the 4 transistors? So you just have to add, okay, C load will be adding all of them. So if you see over here, it will be 1080 P1. Then if you add P2, this is 720. Then N1 is 540 and N2 is 360. Okay, so you add the width of all the transistor. Okay, now what you have given over here, enter your answer as a multiple of C, where C is the output capacitance of a unit NMOS transistor in 180 nanometer process. Okay, so if I have an unit NMOS or unit inverter, okay, not unit inverter, it is unit NMOS. Okay, the output capacitance of this unit NMOS will be what? It will be equal to the W unit of that. Okay, this is 360. Okay, so what we have to find out C load in terms of unit NMOS. So this will be all this divided by 360, and the answer will come 7.5 times C. Okay, because C is the unit which we have taken. So at any node, okay, so whenever you are designing circuits, if you are designing complex circuit, this you have to keep in mind. At any node, what will be the capacitance? If you have to find out, you just have to figure out, okay, how many transistors are connected to that particular node. right? And you just have to add the width of all the transistor. Okay, that will be your unit capacitance. If the question has been asked in terms of some unit inverter or unit NMOS, if you have to, you just divide that. Okay, this is extremely important. Please note that this is extremely important, because in coming lectures we'll be discussing about logical effort, right? And suppose if you are designing very large circuit, if you are designing say a processor, okay, you don't go and size each of these transistor. Okay, a tool does that. That tool is called synthesizer. But suppose if you want to do the same job, how do you do that? That's the question. So you have to find out what will be the sizes of each of this the gate which will be used to design that processor. And how do you find the sizes of each of these gate? You have to actually know what is the unit, what is the capacitance at each of this node you are seeing, right? Because if you know the capacitance, then only you can optimize your design for taking less time. Okay, that is the reason why this question is very important over here. If you, any circuit you have, if you want to find out, okay, what will be the output capacitance of that particular circuit, you should be able to figure out. Is that clear to everybody?
Yes, I have one question. That is, what is the unit of this 7.5? It is femtofarad in
No,
the.
no, no, C, times C, because we don't know the unit, right? So this is also what we have done, we have just normalized it. So if you want
Okay.
to, yeah, if you want to know exact unit what happens, you have to go to the technology to do extremely technology specific. Okay, in 28 nanometer technology, I can say in 28 nanometer technology, if you have say 100 nanometer of width of transistor, okay, so the unit for 100 nanometer, it comes around actually 0.3 femtofarad. This I have simulated, so I can tell you the numbers. I won't tell which technology it is, but yeah, it happens on the order of femtofarad. Okay, so but if you have larger transistor, the capacitance will grow accordingly. Did I answer your question?
Okay. Yes, yes. Thank you.
Yeah, moving to fifth question, again a very simple one. Okay, it is written 7 over here, so don't go by that. It is fifth. uh, which of these defines the propagation delay for falling? If I have to ask you, T falling, okay, TPD falling, TPDF, which of these defines the falling? How do you calculate the falling delay? Can anybody tell me the answer? Quickly, this is an easy question. Falling delay means output is falling, okay? So the input will be rising, okay? The output will be falling. And if you want to calculate, so if this is your input, this is your output, if you want to calculate the delay between them, how do you calculate? Anyone? How do you calculate the delay between
Is it D?
D?
D? Delay, falling delay, so input is rising. Yes.
Okay. Anybody has any other answer? Okay. So in case of an inverter, in case of an inverter only, okay. So these two answers both are correct, because the input will rise and output will fall. Okay. And 50% this particular point and the 50% this particular point, whatever you are getting, okay, this will be delay, TPDF. Okay. In only in the case of inverter, when input is rising, the output will be falling, and you can say the time difference between 50% of the input voltage level and 50% of the output voltage level while input is rising, because that condition is true, or the time difference between 50% of the output voltage level, input voltage level, and 50% of the output voltage level when output is falling. Okay, So in case of inverter, both the statements are true. But if I talk about
No, both the statement is same. Yeah, both the statement is same.
yes, both the statements remains the same in the case of inverter. But in case of any general circuit, right, where this might not happen, this condition might not happen, right? Because suppose if you have multiple inputs and still I want to calculate the delay. So then what we try to do, we figure out or we say that whenever the output is falling, that is the point, and whatever the input, whenever you have provided, right? If the input did not change, means if one of the input did not change, then you cannot find out delay from that particular point. Then there will be some input which will be changing. It can be going from 0 to 1, or it can be going from 1 to 0. Okay, so the answer will be only the fifth one. Okay, when you talk about any general circuit, because whenever you talk about any general circuit and I want to find out falling delay, right, it will be between input and output when output is falling. Okay, it may happen in many of the circuit that input is also falling at that particular point. Okay, but in case of inverter, both the statements are correct, because in the case of inverter it happens, right, input has to rise and output has to fall. So everybody agrees with this point? I assume that everybody is agreeing with me. Okay,
Yes, sir.
thank you. Last question.
Yes.
Last question for today is, if the switching resistance of NMOS transistor with 10 micrometer, okay, is 1 kilo ohm, it means R switching is given as 10, R switching is given as 1 kilo ohm, okay, for W is equal to 10 micrometer. This is the given thing. Okay, then what is the switching resistance for another NMOS which whose width is 25 micrometer? Okay, I have to find out R switching. This is the question for W is equal to 25 micrometer. Okay, so how do you approach this question? Again, you go to unary method. Okay, so what we will do, because you know that, right, you know that resistance of switching is actually inversely proportional to width. Okay, so you can say that R switching is equal to alpha upon width. Okay, so for the first case, R switching is 1 kilo ohm, right, and alpha by 10 micrometer. Okay, so what will be alpha? Alpha will be 10 micrometer into 1 kilo ohm. This will be your alpha. Okay, now if I write same equation, okay, if I write same equation for the second one, then it will be R switching is equal to alpha upon W. So alpha is what? Alpha is 10 micrometer into 1 kilo ohm divided by how much? 25 micrometer. 25 micrometer. Okay, so micrometer goes 10 by 25. This will be 0.4 kilo ohm. The answer is D. Everybody agrees with this?
Yes, sir.
So yeah, for today, yeah, we had this much questions for today, whatever that has been taught in the class. Uh, if you guys have any doubts regarding any of the concepts, you can ask in the WhatsApp group, right? So I have shared the link of the WhatsApp group, and my WhatsApp group's link is also there in the PPT. So if you go to the YouTube channel, okay, you see the video inside, below that you will have the link of PPT also over there. Access the PPT, you can go to the link of the all the materials whatever I am teaching, that is available over there, right? You can watch the video again if you want. Along with that, if you want to ask more question, I suggest everybody to join the WhatsApp group. If you have any question regarding anything regarding VLSI, okay, anything regarding semiconductor, I'm there to answer your question. Okay, I have also added a couple of my students from IIT Gandhinagar, such that if I am not answering, they will answer for you. Okay, so I suggest you to do that. And yeah, just if you don't understand anything, yeah, come and ask. This is the platform for you to ask those kind of questions. Okay, and if you still have question, what you can do, you can mail me over here. Okay, kailash.prasad@itgn.ac.in. To join the WhatsApp group, you just scan this particular code. If you can scan this code, just take a screenshot and scan. You can join to the WhatsApp group. Okay. So that's all for today's class. If you have any question, feel free to ask. No questions? Okay. So as of now, what we are doing the basic questions.
Hello, sir. Sir, today only I joined. As of my doubt is, you are not discussing about week 4 assignment questions, no, sir?
Week 4 will be discussed in the next week.
Next session. Okay, okay. Okay. Whatever the completed assignments only you are discussing, no, sir?
No. Week 4 deadline is before this session, right? So so deadline is later. So we will be discussing concepts regarding that. Okay, and then you
Okay,
can
sir.
attempt the assignment questions. Okay.
Okay, okay. Thank you, sir.
Actually, sir, deadline for week 4 is tomorrow.
Week 4 is
Tomorrow is the dead. Yes, for week 4, the deadline is tomorrow.
Okay, maybe what I will try to do in the next session, I will try to cover both week 4 and week 5, right? So then we are back on track. Okay.
Okay.
I didn't realize that. Okay, but yeah. Anyhow, if you have any question, yeah, you can ask that. Ideally, the expectation is
Sir,
first the session is discussed, and then you can attempt better questions.
hello. Sir, have a question. To design a unit inverter, is it always necessary that NMOS should be unit? It require a unit NMOS and unit PMOS. To design a unit inverter, always it is required that a unit NMOS and unit PMOS. So in that.
So if you want to design a unit inverter, what do you mean by unit inverter? Okay, so unit inverter.
If we are taking 180 nanometer technology or whatever.
If you are taking an 180 nanometer technology, so L will be 180 nanometer, both for NMOS and PMOS, LP and LN. Okay, so in the 180 nanometer technology, if I remember, the width is, I guess, 220 nanometer, the minimum width. Okay, so for NMOS, it will be 220 nanometer. For PMOS, it will be how much? It will be
2 into 220.
yeah, if the mobility ratio is 20, then it's going to be 20. If mobility ratio is anything else, right, it will be that number being multiplied by 220. Okay, so whenever you design unit inverter, NMOS should be unit, and the PMOS should be accordingly scaled up such that beta ratio should be unit.
But it should not be unit. Never be unit.
Yeah, the beta ratio should be 1. The width of the PMOS should be like that, the beta ratio should be 1. NMOS is unit, but the PMOS will differ.
It depends. It may be unit, may not be unit.
Yes. So it may be unit if the beta ratio is also the mobility ratio is 1, right? Instead of 2, if the mobility ratio is 1, then both NMOS and PMOS will be of the minimum size. And in many of the advanced technology, it is actually the case. In that case, it will be unit, but generally the PMOS size is multiplied with the Any more questions? Okay. What about others? Okay, so if you don't have any more questions, thank you everyone for joining. And I suggest everybody, right, you just inform your friends and others also, such that they can also join and leverage the benefit from these sessions. It doesn't matter if they are registered for the course and not. So I'm allowing everybody, right? So you can come here, ask all the questions. You come here prepared with difficult questions, okay? So I'm here to answer all of your questions. So don't worry about the type of question you are having. If you are having basic questions also, I will try to help you. If you are having difficult questions also, I will try to help you in that regards. Okay, so Elmore delay I have not taught over here for an input, what you're saying, an input NAND get. This actually in a greater detail I will be discussing in the next session. Okay, so because of this, I think we are falling 1 week behind. In the next session, I'll be discussing in detail the NMOR delay, right? And the next week question also, the logical effort. Okay, so we will be having entire 2 hour session, and I will try to answer this question for you. Okay, Yamuna, hello. Okay, yeah. So yeah, thank you everyone for joining. We'll meet next week, same time. Okay, so I'm just signing off.